Okay, let's get started on drawing our first set of plate boundaries. Now the first one, we're going to separate the canvas into two pieces. There should be two boxes for you to draw on in your lab book, or you can use two separate sheets of paper, laid out landscape, to do these two diagrams. We're going to start at the top, and we're going to start with divergent boundaries. Okay, two boundaries being separated, pulling apart, or being pushed apart. We're going to start with ocean crust separating, so ocean to ocean divergent boundary. Okay, so just look like our diagram before, we are going to use black for the ocean crust. So you can draw this and color it in, or you can just do the outline. I'm going to do the whole thing, so it's going to be pretty thin, and at the very middle of the page or your canvas, make two angled sections that are sort of in a V shape with a gap between them. Okay, so just like that, that's going to be where the two plates are separating, and then we're going to just kind of blend this down to where the plates themselves would be. Okay. So we're just going to let it kind of trail off the side, kind of disappear into nothing, because we're just focusing right now on these two plates moving apart from each other right here at the center. That's where all the interesting features and all the interesting geology that we're going to talk about is going to be happening. Okay. Now, as two ocean crust sections are being pulled apart, there's this big open fissure right between them. And from it out pumps brand new crust. And it's a rift in the ocean floor that's opening up and letting out lava, which cools and solidifies into the basaltic rock that makes up the bottom of the ocean. So let's add some red in to simulate not only that lava coming out from the crack here, that new crust, okay, but also the lithosphere section right under it. Remember that topmost section of the mantle. Okay, the very bottom part of the lithosphere is actually part of the mantle, and it's going to be right underneath the ocean plate. I'm just going to kind of blend it off into nothing here. We're worried about the features that are right in the center. Okay, and it's okay if the black kind of gets in there like I'm doing here, because the transition section, the zone between the oceanic plate and the top of the mantle, sometimes the ocean plate is kind of melting down into it, but we're going to get back to that here in a minute with the other diagrams that we're going to draw. So this is just the uppermost part of the mantle, the bottom of the lithosphere, that molten part of the Earth's interior. This is where all the material for the new crust that's forming on the surface comes from. Okay, where the plates diverge and that hole opens up, that rift. The lava, well, the magma that's in the mantle below it, magma is what we call lava that's still underground, is forced upward by those convection currents. Let's put an arrow here showing that upward movement of the convection current. Okay, that's what's causing that new crust to come out of the feature there. All right, so we've got our ocean floor are two tectonic plates. They're the ocean crust being pulled apart. Okay, we're going to add some white arrows to show that they're moving apart here in a second. We've got the top of the convection current moving up right at that rift. And there's some really interesting features that happen right next to that rift. And one of the most interesting features is a hydrothermal vent. Now, these are occurring deep in the ocean. These are the mid-ocean ridges, remember? Okay, so we're just going to kind of make a little peek here on both sides. We're going to make a couple of them, both sides of these. And a hydrothermal vent, okay, if we break that word apart, hydro is water, and thermal means heat or temperature. And a hydrothermal vent is just an opening from which very, very hot, superheated groundwater, or in this case, seawater that's being pushed down into the rock because of the ocean pressure, is heated by this close contact with magma, and it erupts back out as a geyser. Of course, this is underwater, so instead of a geyser, we wind up with these features called black smokers. Okay, so we're going to add a little bit of blue underneath these to show the hydrothermal process. May not be able to see that. There's a little blue. I'm just kind of making some cracks down into that ocean plate with the blue. Alright. Yeah, it's not going to show up very well. But you can kind of make a blue smokestack, blue and black coming out of there. Now what's really neat about these black smokers is that some really interesting and unique organisms live there. This is some biologists think that this might be the origin of life on Earth, down here at these black smokers, because the type of animals that live there are chemotrophs. They are using chemosynthesis, okay, using chemicals from that hot groundwater mixed with nutrients from the rocks to live. They feed off of those nutrients and those minerals, and that's how they grow instead of sunlight, because this is at the bottom of the middle of the ocean, so there's no sunlight that actually gets down there. They're living off of the minerals coming from within the actual Earth's crust, which is really cool. And it's some of the oldest, some of the most hardy animals live down there. Bacteria specifically live down there, that's found all over the world in these things. And they can survive in such harsh conditions that biologists think that maybe they were some of the first life forms to evolve. Of course, we may never know the actual truth to that. All right, so this is under the ocean, so we need to add some ocean to it. So let's get some blue, a big brush here, and let's just draw in some waves over it. Okay, now remember, this is all happening at the mid-ocean ridges, deep beneath the ocean. So there should be some water over top of it. So let's put some blue. Okay, let's make some waves at the top, just to make sure we get this point across that this is all happening underwater. Alright. Obviously, our diagram is not to scale. Okay. And we're just going to let it kind of trail off on the sides again. Blend in my black smokers here. Alright, so this is another feature that was not discovered until we used sonar to map the ocean floor. That's when we found these mid-ocean ridges, and the idea of plate tectonics finally made sense. There's another interesting phenomenon which occurs to the ocean floor as you move away from the rift. As you move away from this place where new crust is forming, the age of the rocks becomes older. Okay, because at the very center here we've got brand new, young crust. But as you move further and further away from it, the crust gets older. And older crust, okay, is crust that formed millions of years ago. But what's interesting is that the ocean floor is actually relatively young. If you remember that we talked about how the ocean floor subducts underneath continental crust, at the very edges of the oceans, it's all subducting underneath. So we don't have ocean crust that's very old. The oldest rocks on Earth are actually on the continents because of that, because the crust of the ocean is dense, it's very heavy, it's very thin, and it's forced underneath the continental crust. So the ocean crust is constantly being recycled, and it's relatively young. Now, what's also interesting in geology, one of the things that led to the idea of seafloor spreading, which supports plate tectonic theory, is that the crust, when it forms, has iron and other minerals in it which are magnetic. Okay, and we all know that a magnet points to north, right? If we have it on a compass or as a compass. Okay, so if the little magnetic minerals inside these rocks align themselves to magnetic north. What's interesting is magnetic north has not always been north. Magnetic north as it is now, when you have a compass, it's going to point towards the North Pole. But the poles, the magnetic poles, will switch periodically through Earth's history. And we wind up with a pattern in those minerals. As we move away from the center of these mid-ocean ridges, the crust gets older as we move farther away. And on both sides of this rift, that magnetic pole pattern flips back and forth, and it's a mirror image of both patterns on both sides. So that means when crust is forming at the center, it moves outward. As new crust forms, it moves outward. And it helps prove or support the idea that these oceanic plates are diverging and moving over time. Okay? So this is a diagram showing the divergent plate boundary of oceanic crust separating and forming new ocean crust in these mid-ocean ridges. Okay, we've also got these little hydrothermal vents happening down there as well, okay, which provide nutrients and life-giving chemicals to those chemotrophs, chemosynthesizers. Alright, so right at the center we've got new crust, lava coming out, forming that basaltic oceanic crust. And of course these two plates are moving apart. Okay, so let's add the diagram labels to it. Okay, you're going to put ocean crust, divergent should be our title. Okay, ocean to ocean, divergent. We're going to put a big white arrow going to the left and to the right for both of these. We could add in a red arrows underneath to help remind us that it's the convection current that's helping this process along. Okay. So we can put arrows on the on the oceanic crust as well as in the mantle underneath it. Okay, and those plates are moving apart, diverging. At the center, I want you to label new crust. Okay, new crust. And then older crust with arrows moving apart towards that way and towards this way, towards the right and left. Older crust. Okay, and label these hydrothermal vents or black smokers. Okay, and that finishes our first diagram. Real simple, real straight to the point. Ocean and ocean, divergent boundary. Okay, we're going to move to the next diagram here in a moment. We're going to do continental divergent boundary on the bottom.